All righty, lads and ladies, welcome back to Calc 2. Today we are going to play around with some more of the concepts and problem types from section 11.9. So last time on Wednesday, we learned how to integrate and differentiate power series. And we learned how to use that geometric series trick to come up with power series for rational functions. I want to look at a handful of slightly more difficult problems today. And get you used to some of the sort of standard series manipulations that arise in these situations. Let's get this all fired up. Okay. All right. So this, of course, is MAC 2312, section number 004, which is Calc 2, and the date today is the 25th of March, 2022. Today, more power series problems. Specifically from like, I'll do some 11.8 and some 11.9 stuff. I want to begin with a problem that's kind of similar to a homework question that you have, because it's not a calculation thing, it's very much a concept thing. And it's not very obvious. So now that you guys have had a little bit of time to kind of sit and look at and think about those problems, I thought it would be interesting to work one like this with you. So let's start by saying something like, suppose sigma n from 0 to infinity Cn times 5 to the n converges, and sigma n from 0 to infinity Cn times negative 8 to the n diverges. I'll ask a few questions about this. What can we say about sigma n from 0 to infinity Cn times negative 3 to the n? What can we say about sigma n from 0 to infinity Cn times 10 to the n? Let's say negative 6 to the n. Each of these on their own would make a good test question. And the trick, although it might not look like it, the trick has everything to do with thinking about power series, even though there are no power series here anywhere. Specifically thinking about the possible interval of convergence and how this information, this guy converging and this guy diverging, gives me kind of a possible range of sizes for the IOC. So when I say we're going to be thinking about a power series, what power series? Well, all of these can be thought of as specific values of a power series. namely, let's say consider the power series sigma n from 0 to infinity Cn times x to the n, whose center is 0. You see how every one of these series and these two series up here are sort of special cases of this power series. If you plug in 5 for x, you get this guy, which we're told is convergent. If you plug in -8 for x, you get this guy, which we're told is divergent. And each of these would come from plugging in like -3, 10, or -6 for x. So in order to say whether the power series in A, for example, converges or diverges, it suffices to know whether -3 is in or out of the interval of convergence. So the IOC for this power series must include 5, because I'm told that this series converges. And must not include x equals -8, because that other series diverges. So let me sketch a possible interval of convergence here. Let's just see what we can say about these things. I know that +5, which I'll say is like right here, has to be in the IOC. And -8, which I'll say is over here, has to be outside of the IOC. Because the interval of convergence is always symmetric about 0, symmetric about the center, I should say, and the center here is 0, I know that this IOC, this stuff is all in the IOC because my center is here. In other words, the radius of convergence might not be equal to 5, but it has to be at least 5, right? Greater than or equal to, which means that I have to extend at least 5 in this direction as well. So everything that I've shaded in red here, everything that I've shaded in red here has to be in the IOC. So let's think about this guy for a minute. The series in A, is it convergent or divergent, and why? This guy, convergent or divergent? Very good. Yes, I know that this first series sigma Cn times -3 to the n, sum from 0 to infinity, must converge. Because x equals -3 must be in the IOC. -3 is like right here. I know that the interval of convergence is centered at 0 and extends to the right by 5 units. Because the interval of convergence is always symmetric about the center, if it extends to the right by at least 5 units, it must also extend to the left by at least 5 units. -3 being right here must be in the IOC. Everybody follow that logic? Series centered at 0. 5 is in the IOC. So the distance, right, the worst case scenario here is that 5 is the endpoint for the IOC. The endpoint might be over here at 6 or 7 or 5.9. But the worst case scenario, the smallest the IOC could possibly be, is from -5 to 5, because I know that the series is centered at 0 and that 5 is in the interval of convergence. So the interval of convergence must stretch at least 5 units to the right. And by symmetry, interval of convergence always symmetric about the center, the IOC must stretch at least 5 to the left. Since -3 is in this worst case scenario, IOC, this series must converge because this series is this power series with -3 plugged in for x. Let's take a look at part B. I'm going to redraw the IOC. 0 here, 5 here, -8 here. I know that my IOC has to go at least from -5 to 5. I know 5 is included. I'm not sure if -5 is included or not. Worst case scenario would be that -5 is not included. I'm told that sigma Cn times -8 to the n is divergent, right? So -8 is not in the IOC. And that means that the radius of convergence must be strictly smaller than 8. Actually, I guess less than or equal to. -8 could be an endpoint that is excluded. But if the radius of convergence was 8 or larger, right, then this would have to extend out past 8, past -8, which would mean that -8 is in the IOC. But I was told that sigma Cn -8 to the n diverges, which means -8 cannot be in the IOC. So the radius of convergence could stop like here. That's possible. The radius of convergence could be something like 7. But what this tells me in particular for part B is that ten can't possibly be in the IOC. Because if 10 was in the interval of convergence, it would have to stretch at least out to here, which would mean it would have to stretch at least out to here. And I know that that's not the case. right? So your largest possible radius of convergence here has to stop before you get to -8. So r is less than or equal to 8, which means we can't possibly come out past 8 here. So 10 can't possibly be in the IOC. So this is the solution for part B. I think this is fun because there's zero calculation here, right? All I'm doing is thinking about the possible intervals of convergence for this power series. Questions on the logic in part B? Okay. Finally then, in part C, oh, sorry, so sigma, in part B here, the wrap up here would be, so sigma n from 0 to infinity, Cn times 10 to the n must diverge. And then finally, we wanted to ask, sigma n from 0 to infinity, Cn times -6 to the n. And again, we can kind of reuse this picture. I know that r has to be at least 5. But no bigger than 8. The largest possible IOC is the open interval from -8 to 8. The smallest possible IOC is the right closed left open interval from -5 to 5. So let's just recap what we have. The largest smallest is which one did we say for sure converged? We're given that 5 to the n. All right, so that would mean -5. I suppose this one, let's see, we were told that sigma is at 8 to the n or -8 to the n diverges. Yeah, so the largest possible, this could actually be closed at 8. Largest possible IOC, -8 to 8. Smallest possible IOC, -5 to 5. Largest possible is -8 to 8 because I was told that the series diverges when you plug in -8. So this can't possibly be in the IOC, which means the ROC must be less than or equal to 8. And how do you maximize that? Well, if I know -8 is not in there, then the ROC could possibly be equal to 8, just divergent at the left endpoint. So the largest possible would be -8 to 8, and we don't know what happens at 8 itself. We could converge, we could diverge. So the largest possible is this guy. Similar logic, we were told that the series converges when you plug in 5. So the radius of convergence must extend at least out to 5, which means it must extend at least out to -5. But at the end point, we don't know what happens. We were told that the series converges when you plug in 5, but we don't know what happens here. So the smallest possible is this guy. Where does 6 live? It's outside the smallest possible IOC, which means we don't know for sure, so there's no guarantee that sigma Cn 6 to the n converges. But also, x equals 6 is inside the largest possible IOC. So there's no guarantee that series sigma Cn 6 to the n diverges. So in other words, with the information we've been given, oh, negative 16, sorry. With the information we've been given, I cannot guarantee that this series, the series in C, diverges or converges. I can't say for sure either way. I do not have enough information. I do have enough information for the first two, and that's the part that I think is kind of cool, kind of exciting. And I just wanted to show you what we can do with these, just how powerful thinking about the symmetry of the IOC can be. So in parts A and B, we were able to say for sure that the series in part A converges because he is this power series with x equals 3 plugged in, and I know that 3 has to be in the interval of convergence. In part B, I was able to say that the series necessarily diverges because 10, right? This series is my power series with x equals 10 plugged in, and I know that there's no possible way for the IOC to stretch all the way out to 10. So kind of outside the interval from -8 to 8, I know everything diverges. You know, any x value you were to plug in out here, you will get a divergent series. All this divergent, divergent. Anywhere outside the interval -8 to 8. And I know anywhere inside the interval -5 to 5, you're guaranteed to converge. But in between those two, from -8 to -5 and from +5 to +8, I cannot say what's going on. Could go either way. So I'll say one more time, problems like these I enjoy a lot, and I think they are a very good check on how well you understand intervals of convergence. So problems like these have a way of showing up on the exam. All right. Questions on any part of this problem? And left open, right closed. Yeah, so I was told that the series diverges when we plug in -8, which means -8 itself can't be in the IOC. So the largest possible one is open on the left, closed on the right, -8 to 8. I was told that the series converges when we plug in 5. So 5 must be in the IOC. So the smallest possible would be left open, right closed, -5 to 5. Yeah, even the largest possible IOC doesn't have a bracket here because the problem told us that this series diverges. which means -8 can't possibly be in the IOC. And this series told me that 5 must be in the IOC. So kind of here we're asking, what's the largest interval centered at 0 with radius 8 that does not include the number -8? And that's this guy. Here we're asking, what's the smallest interval centered at 0, radius 5, that does include +5? Variations on these problems could have this one closed on the left and open on the right, or this one closed on the left, open on the right. There's no, the structure of the problem doesn't inform us the shape of these intervals like with brackets or parens. You have to look at the specifics. I could rewrite the problem slightly so that this one is closed and this one is open. Or the same for the second guy. It's a good question. Any other questions on this? Okay. There's something else kind of fiddly power series stuff that I want to share with you because you need it for one of the problems in 11.9, and it's an important technique in differential equations and elsewhere. And this is the idea of something called an index shift. I'll say we're talking about index shifting. And sort of to prime you for this, I want to talk about the idea of a dummy variable. A dummy variable is a variable where the symbol you use doesn't matter. For example, the integral from 0 to 1 of t squared dt, the t there is a dummy variable because this is going to be the same as the integral from 0 to 1 of x squared dx, and that's the same as the integral from 0 to 1 of y squared dy. So these are all dummy variables. All of these things are equal to 1/3. So here, t, x, and y are what are called dummy variables. Generally, what works for integrals works for series as well. If I talk about sigma n from 1 to infinity, 1 over n squared, that's the same as sigma k from 1 to infinity, 1 over k squared, and that's the same as sigma I from 1 to infinity, 1 over I squared. Right? It doesn't matter what symbol I'm using there. Each of these represent a sum, right? 1 plus 1/4 plus 1/9 plus 1/16, and so on. It doesn't matter what symbol I'm using here. These are all just ways of writing 1 plus 1 over 2 squared is 1/4, plus 1 over 3 squared is 1/9, plus 1 over 4 squared is 1/16. All of these represent the same sum. So in other words, if I have a series written in terms of k, I can change the k to an n, and it doesn't change anything. right? Just relabeling the symbol doesn't have any effect because it is a dummy variable. Why is this important? Well, you know how you learned U sub for integrals? There's a kind of U sub for series, and it's called an index shift. Only the thing is, because the variables in series are dummy variables, it's pretty common for people to use the same symbol for the U sub as for the original. I'll show you what I mean. Index shifting is like U sub for series. Let me show you an example. So I might want to shift this so that it starts at 1. Scroll down like this. So shift to make the series start at n equals 1. So here's how I would do this. I would let k be equal to n plus 1. This is my like U sub. This means if you subtract 1 from both sides, k minus 1 would be equal to n. So there's no like differential dk or anything you need to calculate here, because k is a whole number. And we change our bounds. When n is equal to 0, k would be equal to 0 plus 1, which is 1. And when n is equal to infinity, k would be equal to infinity plus 1, which we all learned in kindergarten is the same as infinity. So sigma n from 0 to infinity, negative 1 to the n over n plus 1 is the same as sigma k from 1 to infinity, negative 1 to the n. Well, n is k minus 1 divided by n plus 1. Well, n plus 1 is k. And then here's where I'm going to use the fact that n's and k's are dummy variables. I'm going to go ahead and say, well, I could just call this sigma n from 1 to infinity, negative 1 to the n minus 1 over n. Because k and n are dummy variables. So that's it. I shifted the series to start at n equals 1. You can also shift the series down to make a series that starts at 1 start at 0. And that's what you have to do at one point in your homework. So I'm going to work a problem similar to the one from your homework set. And you'll see what I mean. But this simple example here is a good one to start with. So are there any questions about this? Start. Word here, start up. Some people don't have a problem going straight from this to this. They don't need to write anything down. They're just super comfy. And if that's you, that's fine. But if you want to kind of follow the mechanics and be very careful about it, try writing it out just the same way you would write out a u sub for an integral. It's the same thing. Okay. So I'm going to tackle a problem now that is very similar to one in your homework. And after we find the desired power series, I'm going to index shift it to make it start back at 0. I'm going to go ahead and turn the page. So I want to find a series starting at n equals 0, so like sigma n from 0 to infinity, for this function. And the trick here is going to be to differentiate another power series to get the series for this function. Now here's how I like to solve these. Thinking about the chain rule, right? This is 1 plus 5x to the negative 2. I would say that this thing, f of x, looks like, or reminds me of, the derivative ddx of 1 over 1 plus 5x. This is the step that people seem to have a hard time with. But just follow me for a second here. Right, this thing, without the derivative, just this thing, is 1 plus 5x to the negative 1. So where am I coming up with this? Well, I'm thinking like 1 plus 5x to the negative 2. You know, if you differentiate something with a negative 1 power here, you expect to get something with a negative 2 power there. So that's where I'm coming up with this guess. This is basically just a guess. Now I'm going to go ahead and compute this, and I'll see how far off I was. And that will give me the setup for my power series. So what is this derivative? If I actually take it, I get negative 1 times 1 plus 5x to the negative 2. It's differentiating the outside, right? Bring down the power, subtract 1 from the power. And then I have to multiply by the derivative of the inside, which is 5. So this is negative 5 times 1 over 1 plus 5x all squared. So take this thing equals this thing and divide both sides by negative 5. That means that negative 1/5 times the derivative of 1 over 1 plus 5x is equal to 1 over parentheses 1 plus 5x all squared. And that's my function. This is f of x. Why is this useful? Well, I'm trying to find a power series for this. And what this equation here says is that to get a power series for this guy, I can start with a power series for this, take a derivative, multiply by -1/5, and that will be equal to the function I'm looking for, i.e. my function f of x, the thing I want the series for, is -1/5 times the derivative of 1 over 1 plus 5x. So I'm going to find a series for 1 over 1 plus 5x, differentiate that, then multiply by -1/5. That will be the series I want. The only thing is that it's not going to start at n equals 0, and you'll see why. So to see that, let me go ahead and work the problem. -1/5 ddx. I want to find a series for this guy. Let me do that off to the side here, because it's just the geometric series trick. 1 over 1 plus 5x is 1 over 1 minus -5x is sigma n from 0 to infinity, -5x to the n, which is sigma n from 0 to infinity, -1 to the n, 5 to the n, x to the n. So this is ddx of sigma n from 0 to infinity, -1 to the n, 5 to the n, x to the n. When I take the derivative of this series, we know that all this stuff is basically constant. I'm just differentiating x to the n. But because this series starts with the constant term 1, I have to bump the starting index up by 1. So I'll get -1/5 sigma n from 1 to infinity, -1 to the n times 5 to the n times n x to the n minus 1. Remember, this n equals 0 jumps up to an n equals 1 when we differentiate through a series that begins with a constant term. The starting term for the series, if I write out the first few terms here, this is 1 minus 5x plus 25x squared minus blah, 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 blah. So that very first term does have, the very first term here is constant. And that's what tells me when I differentiate, I have to bump this n equals 0 up to n equals 1. That was that rule that we discovered or discussed last time. When you differentiate a power series, you have to bump up the starting index if and only if the original power series begins with a constant term. Let's pause for a second. Questions getting up to here? Questions on where this blue highlight box came from? In terms of creativity, this is the hard part. So don't be shy. I want to know what you're thinking, even if it's just what the fuck. Feel free to throw out a what the fuck if that's how you think. Okay. Questions getting from here to here. In other words, questions finding this series. Okay, questions going from here to here, taking the derivative of that power series. Why did I not differentiate 5 to the n? Right, the derivative of 5 to the n is 5 to the n times the natural log of 5. Where's my natural log of 5? Didn't I have to differentiate that piece? Very good. Very good. So it was a DM, and I want everybody to hear this answer. The reason I don't have to differentiate this piece or this piece is because they don't have any x's in them. This derivative is d dx. I'm taking the derivative with respect to the variable x. So this operator, d dx, sees all this stuff as constant multiples. The only thing that he can actually see when he looks through this expression, the only piece that he can see is the x to the n. He's blind to everything else. So it's like you just took the derivative of x to the n, and the derivative of x to the n is nx to the n minus 1. Power rule. Okay. I can push the negative 1/5 inside the series, and I get sigma n from 1 to infinity. I'll write that as negative 1 times 1/5. And then you've got negative 1 to the n times 5 to the n, and then nx to the n minus 1. Everybody here is multiplying. So I can put these two like terms together. And I can put these two like terms together. And I get sigma n from 1 to infinity, negative 1 to the n plus 1 times 1/5 times 5 to the n is 5 to the n minus 1 and x to the n minus 1. And on a test, if I asked you for a power series for this function, I would be very happy with this answer. This is a great answer. But this question explicitly said they want the series to start at 0. And this series starts at 1. And some of your WebAssign problems are like this, where the answer box like already has a sigma n from 0 to infinity in it. So I need to index shift this down. My series starts at 1. I want it to start at 0, so I'm going to let k be n minus 1. This is our index shift. And I'm going to write it all out. If k is n minus 1, then k plus 1 is equal to n. And changing our bounds, when n is equal to 1, k is 1 minus 1, which is 0. And when n is equal to infinity, k would be infinity minus 1, which is definitely still infinity. So this new series would be sum k from 0 to infinity, negative 1 to the n plus 1. Well, n is k plus 1, so this would be negative 1 to the k plus 1 plus 1, which is k plus 2. 5 to the n minus 1, well, k is n minus 1, so that's 5 to the k. N is k plus 1, so this is going to be k plus 1 times x to the n minus 1 is k. A couple other little things we can do here. Negative 1 to the k plus 2 is negative 1 to the k times negative 1 to the 2. And negative 1 to the 2 is just 1. So this is the same as negative 1 to the k. Means I can rewrite that very first piece as just -1 to the k. And then I'm going to switch everything back to n's because dummy variable. So I get sigma n from 0 to infinity, -1 to the n, 5 to the n plus 1, x to the n. And that would be your final answer here. Now, I may be writing more steps than you would need to write. Yeah, I think with a bit, certainly with more steps, if I was solving this just for myself, I would not write out this many steps. I would probably, like everything above here, I would need to write. Definitely, I would write this and this and this. From there, I would probably jump to here. From there, I would probably jump to here. But with practice, right? This comes with practice. So the first few times you do it, please be very, very careful. Use this as a pattern you can follow. You have a homework problem very much like this. They also ask for the second derivative. Basically, they ask you for a 1 over 1 plus x cubed or something like that. You should be able to get by differentiating again. But this is the vibe. This is how we do this stuff. Last call for questions on this. Okay. There's some other cool stuff we can do now that we couldn't do before. There are a lot of integrals we can solve now that we couldn't solve in the past. So this is sort of the big payoff of learning power series, is that you remember from the start of the course, there are a shitload of functions that you just can't integrate. Remember in section 7.5, we talked about like natural log of x over x, or e to the x squared, or sine x over x, or sine of x squared. There's a ton of things where there just is no nice way to write an antiderivative for this function. You can always take the derivative. Derivatives are easy, but integrals can be extremely hard. And many integrals can't be solved in terms of what are called elementary functions. Well, now that we have access to power series, we have access to non-elementary functions, which means we have access to solutions to problems like this. The trick to all these, where like here's an integral evaluated as a power series, you have to write the function inside as a power series and then integrate that series. So I'll begin here by saying, recall. One of our very important power series from last time, I'm going to write it in terms of the variable u. We found a power series for the inverse tangent function. And if I just use the variable u, instead of the variable x, that series is sigma n from 0 to infinity, 1 to the n over 2n plus 1 times u to the 2n plus 1. If you plug in x squared for u, we get the series inverse tangent of x squared equals sigma n from 0 to infinity, -1 to the n over 2n plus 1 times x squared to the 2n plus 1. And I can clean that up. I'll write this as nicely as possible. So that's sigma n from 0 to infinity, -1 to the n over 2n plus 1, x squared to the 2n plus 1 is x to the 4n plus 2. We're raising a power to a power, you multiply the powers. So 2n plus 1 all times 2 is 4n plus 2. Questions so far? Okay. Therefore, the integral of the inverse tangent of x squared dx is the integral of this series. Integral of sigma n from 0 to infinity, -1 to the n over 2n plus 1, x to the 4n plus 2 dx. And very similar to how when you differentiated a series, a power series, the derivative only sees the x's, well, the integral only sees the x's also. So like to this integral, this is what he sees. He just sees, oh, I'm an integral, I'm an integral, I'm an integral, I'm an integral. Here's an x to the 4n plus 2. That's a power rule integral. I'm integrating dx, so all I see is him. I can't see any of the shit under the pen. All the integral sees is this. And the power rule for integrals, the power rule for integrals says, if you're integrating just a power of x, you add 1 to that power. So this is going to become x to the 4n plus 3, and then divide by that new power, right? Just like when you integrate x squared, you get 1/3 x cubed. If you integrate x to the 4n plus 2, you get 1 over 4n plus 3 times x to the 4n plus 3. Remember with series, when we integrate them, we write the plus c out front, so we don't confuse it for being inside the series. It's not. All the sigma stuff and the coefficients just come along for the ride. The integral of x to the 4n plus 2 is 1 over 4n plus 3 times x to the 4n plus 3. And that's it. That's your answer. You can pretty it up a little bit. By writing all the coefficient stuff together. And you get this. That is it. That's your answer. There's no need to solve for c here, because I was given, the problem I was given was this indefinite integral. They didn't say find a series for some function. They said find a series for this indefinite integral. And we know when we do indefinite integrals, we get a plus c. So he's chilling. You're done. Now looking forward to what we're going to be doing next week, I'm going to write out the first few terms of this series and then look at some graphs in Desmos. So if I start actually writing out the terms of this series, when n is 0, you have 1 over 1 times 3 times x cubed. So this is going to be, first term here is 1/3 x cubed. When little n is equal to 1, you get minus 1 over, let's see, this would be 3 times 7, 21, and then x to the 4 plus 3 is 7. The next term would be plus, right? -1 to the 2 is 1. 2 times 2 plus 1 is 4 plus 1 is 5. 4 times 2 plus 3 is 8 plus 3 is 11. So that's 1 over 5 times 11 is 1 over 55 times x to the 8 plus 3 is x to the 11. And the next term would be negative and goes on like this. Remember, power series are polynomials, infinitely long polynomials, just big polynomials. And nothing can stop me from writing out the first few terms. The dot dot dots here mean, yes, it goes on like this forever. Yes, there are a lot of other terms. But remember, if a series converges, then the high order terms, the late terms in the series, should all be very small. So by far, the biggest part of this series is the first term. This next term is much, much smaller. Remember, x here is going to be between -1 and 1. When you raise a number like 1/2 or 1/3 or 2/5 to a number like 7, you get a very small thing. So this is the biggest term. This is the next smallest term. This term is much, much smaller still. And all of these terms are in fact tiny. They have large powers of x, so they are tiny, tiny, tiny. When human beings decided they wanted to go to the moon, we realized we're going to need some pretty accurate solutions to certain differential equations, complicated differential equations that you can't solve using the methods learned in MAP2312, except the method of Frobenius, which involves power series. Generally, to get to the moon, you need like second order precision, meaning you need like the first 2 terms of the power series. 3 terms of the power series is considered overkill in most engineering circumstances. What I want to do is compare this function evaluated by Desmos as a graph to this function. And the way I'm going to do that is by asking Desmos to graph both of them. And I want you to watch this. Now, Desmos can only do definite integrals, so I have to type it like this. There she is. I'm going to ignore the plus c here, basically just assuming that c is 0. That's, because I put a 0 in down here. Look how well, even just with the first 2 terms, look how well this blue is gluing itself to the red. And remember that the interval of convergence here is the interval -1 to 1. So on that interval, god damn, that's good. This blue is so close to the red, just with the first 2 terms. If I add the next term, it gets even better. Actual, approximate. Actual, approximate. Outside the interval of convergence, the blue doesn't do a good job at all, right? Outside of -1 to 1, the blue's like doing whatever the fuck it wants. But if you stay inside the interval of convergence between -1 and 1, the blue and the red are virtually indistinguishable. Same function. If you get way, way, way in here, especially close to the endpoints, you will see some slight difference, right? Slight difference. But it's a very, very small difference. And if I were to use more terms, that difference would get even smaller still. This is why we care about power series, because if I wanted to do something with the red function, that's an extremely hard function to work with. Extremely hard to work with. But the blue function is a friggin' polynomial. It's really easy to work with. So that's the game. The first few terms of a power series are called Taylor polynomials. And next time, what we're going to learn is a theorem called Taylor's theorem. I won't spoil that for you just yet. So instead, in these last few minutes, let's see, So comparing graphs, we see that on the interval -1 to 1, the functions y equals integral tan inverse x squared dx and y equals 1/3 x cubed minus 1/21 x to the 7 plus 1/55 x to the 11 are basically indistinguishable. Basically the same. And of course, that's what we want, right? This power series is supposed to represent this function exactly. And the first few terms are good enough to get a very, very strong approximation. The last kind of cool thing that we can do with power series now that we wouldn't have been able to do before is to find the sum, like adding up certain series. Before, the only series where we could find the sum were either geometric series or telescoping series. All the other series that we worked with back in chapter 11, we couldn't figure out what they added up to. We could do convergence tests and figure out whether they converge or diverge, but we couldn't tell you the sum. So the last little thing I want to do here is use power series to sum certain series. So let me put it like this. Let's see. Yeah. I don't know. Should we do one more? Yeah, I'm good for it. So use your knowledge of power series to find the sum. Both of these are convergent series. They're both conditionally convergent, but they both converge. We're not going to use any convergence tests. I know these two series converge. What I want to do is find the sum of the series. It's true that they're both alternating series, so I could use the alternating series estimation theorem to approximate the sum, but I want to find the exact sum. And the trick is to recognize both of these as power series with something plugged in. Both of these are specific values of a power series. The natural log of 1 plus x, remember, has series sigma n from 0 to infinity, -1 to the n over n plus 1 times x to the n plus 1. Which I can index shift into the series sigma n from 1 to infinity, -1 to the n minus 1 over n times x to the n. So plugging x equals 1, we get the natural log of 1 plus 1 is equal to sigma n from 1 to infinity, negative 1 to the n minus 1 over n times 1 to the n. But of course, 1 to the n is just 1. So this is sigma n from 1 to infinity, negative 1 to the n over n. Oh, sorry, n minus 1. Negative 1 to the n over n. And that is S. I.e., S is the natural log of 2. The natural log of 1 plus 1. How did I do this? I look at this guy and I go, ooh, that reminds me of the series for the natural log function. This reminds me a lot of this. So let me see if I can make this look even more like that with an index shift. I can. And then looking at this, realize, oh, if I plug in 1 for x, this will become this series. So it must be the natural log of 1 plus 1, the natural log of 2. Now here the series t, when I look at that guy, what I see is that downstairs I can factor out a 4. It's negative 1 to the n over 4 times 2n plus 1. So that's 1/4 sigma n from 0 to infinity, negative 1 to the n over 2n plus 1. And what power series does that remind you of? Yeah, there's no x's here, but these coefficients, these numbers are the same as the coefficients from the inverse tangent power series. So let's say, and we know the inverse tangent of x is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 x to the 2n plus 1. So the inverse tangent of 1 is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times 1 to the n, which is this guy, because 1 to the n is just 1. Therefore, t is 1/4 sigma n from 0 to infinity, negative 1 to the n over 2n plus 1, which is 1/4 times the inverse tangent of 1. And the inverse tangent of 1 is pi over 4. So this is 1/4 times pi over 4, which is pi over 16. So that second series has to add up to pi over 16. This is such a common trick that it's also likely to show up on your test, right? Using power series to sum or find the sum of other series. So recognizing these other series as power series with something specific plugged in. We will look at more of these as we broaden the scope of power series that we know. Next time, I'm going to show you Taylor's theorem. So just one last little thing I want to share with you before we go, just in preparation for next time. The first, right, so f prime of x, this is the first derivative. F double prime of x is the second derivative. F triple prime of x is the third derivative. But what notation could I use for the like 50th derivative? So yeah, that's correct figures. So one of the things that we're going to need in order to discuss Taylor's theorem is some notation for higher order derivatives. I don't want to write 50 primes, f with 1, 2, 3, 4, 50 primes. Of x. This is terrible notation. I wouldn't want to write 50 little dashes there. So instead, the standard notation you write f1 for f prime, f2 like this for f double prime, f with a superscript parentheses 3 for f triple prime. And in general, you write f superscript parentheses n of x for the nth derivative of f of x. So super quick example. I wanted to find f5 of x for f of x equals x to the 7. I would say, okay, well, f1, that's 7x to the 6. f2 is 7 times 6, x to the 5. f3, that's 7 times 6 times 5, x to the 4. f4 would be 7 times 6 times 5 times 4 times x cubed. So the fifth derivative, f5, would be 7 times 6 times 5 times 4 times 3 times x squared. That's the idea. And if you see something piling up here that looks like it could be or eventually lead to a factorial, then you're correct. And we will explore that and more on Monday of next week. So between now and then, please work hard on that homework. Make sure you get very comfortable doing things like integrals as power series, integrating and differentiating power series in general, and make sure that that geometric series trick, the thing that we kind of use as our foundation in 11.9, feels like water to you. It's just very, very easy. You hardly have to even think about it. All right, that's it from me. I am doing a round of kind of makeup tests today for some people who couldn't come earlier in the week. So today's office hour is going to be a quiet one, but I will be there. And if there's anything else you need from me, you can send me a Canvas message or an email. All right. Take care, guys. Work hard.